Thank you. Well, it's a pleasure to be here to talk to you about looking for life on Mars. It's a very exciting time for space exploration at the moment, and the search for life elsewhere in the solar system or even elsewhere in the universe is really on at the moment. And in fact, the first slide shows you a few possibilities in our own solar system where there could either have been or could even be life now. So on the top left, there's Mars, of course, about half the size of the Earth, and that's important when we come to speak about the magnetic field in a minute. There's also, slightly smaller in the lower left, Europa, so that's one of the moons of Jupiter. That has a water ocean underneath an icy crust, and missions like Europa Clipper that NASA has going fairly shortly, and also the European Space Agency's JUICE mission will be flying past Europa on its way to Ganymede, so really something to look forward to. Enceladus at the top right there, of course, that was visited by the Cassini-Huygens mission, and Cassini made some amazing discoveries at Enceladus. And in particular, water coming from those icy vents at the bottom there of the image. And so water, again, from a subsurface ocean. And that subsurface ocean is not only water, but it's salty water coming out. There's also some sand in it, silicates, and that's indicative of hydrothermal activity at the bottom of a subsurface ocean. There's also hydrogen, and that's one of the things you need for life. So those two really, Enceladus and Europa, those are possibilities for life, perhaps even now. Titan there is an amazing place as well. That has a thick atmosphere. It's the only solar system moon with a thick atmosphere, one of Saturn's moons. We discovered some very large prebiotic molecules at the top of Titan's nitrogen and methane atmosphere with some of our work with Cassini. And Huygens, of course, landed on Titan. So really amazing target and something to go back to in the future. And again, it has a subsurface ocean, and the possibility there perhaps is for life as well, although it is colder, so it's a little bit smaller than the other images. Also, just last week, the possibility of life in the clouds of Venus, which you can see there on that image on the bottom right. That seems to be a possibility as well, because phosphine was discovered, and one of the possibilities for that may be the presence of life in those sulfuric acid clouds. The sulfuric acid clouds make it fairly unlikely, but nevertheless it joins those other targets as exciting places to look for life in the future. So next slide actually sort of takes us, it's a bit of sort of history, going back into Mars's history. So 3.8 billion years ago, bear in mind the solar system, the rest of the planets, and including Mars, formed about 4.6 billion years ago. So 3.8 billion years ago, we know that there was water on the surface of Mars. The evidence for that has been building up, with including images on the top left there. So that's a sort of close-up images of one of the outflow channels on the surface of Mars. That's indirect evidence for water on the surface. We're getting more direct evidence now, but that's some of the indirect evidence. And that started really with the Viking mission in the 1970s. But since then, there have been a lot more missions, and we'll talk about some of those in a moment. So Mars used to have water on the surface. Mars also used to have a magnetic field. This image here shows what happened when the first magnetometer was actually taken near enough Mars to be able to make measurements. And so in the background, the image, the color scale, shows you an altitude map of Mars going from low altitude, which are the blue, through yellow and red, all the way up to white. And those are going up in altitude. But over the top of that, the white and black contours show magnetic field, and those are sort of linked magnetic fields. Those are the signs of crustal magnetic fields, which were there from the time when Mars was forming 3.8 billion years ago. You can see those white and black contours are concentrated in the southern hemisphere of Mars. That's the old terrain, it's very cratered, and from that cratering density, you can tell that surface is about 3.8 billion years old. So that magnetic field was trapped from a time when Mars actually had a global magnetic field. But suddenly that stopped just after 3.8 billion years ago, and that allowed the atmosphere to escape, which we'll get to in a minute. But the third difference of Mars then compared to now is that Mars had volcanism. And that is an image of Olympus Mons, which is the biggest volcano in the solar system, 600 kilometers diameter. It's a shield volcano, and it's a sign of huge volcanic activity going on Mars at that time. So Mars was quite different. It had water, it had a magnetic field, and it had volcanism. So it's a little bit like the Earth at the time, about 3.8 to 4 billion years ago. That's about the time that life was starting on Earth. So we think it's possible that life perhaps could have started on Mars. So Mars now, though, the volcanoes are extinct. There's no large-scale magnetic field, no dipole magnetic field like we have at the Earth. There's only these remnant regions or crustal magnetic field regions. And there's a very thin atmosphere. That atmosphere is only 7 millibars, so that's less than 1% of the Earth's atmospheric pressure. It's a carbon dioxide-rich atmosphere, so not something we could breathe, and certainly the pressure is much too low as well. It's also very cold and dry, so that bottom image gives you an idea of the sort of desert-like features which Mars has on the surface. That actually is from Mars Pathfinder several years ago. But the surface of Mars is really harsh for life now. So as well as that thin atmosphere, which means that, for example, cosmic rays and ultraviolet can penetrate through the atmosphere to the surface, making the surface very harsh for life. So that surface is very harsh. Also, it's extremely cold on Mars. So on a good day on Mars, it might be 10 degrees centigrade, something like that, on the sunlit side of Mars. But on the night side, every night it can get down to minus 110, minus 120 degrees centigrade. And so that gives you the sort of engineering constraint for if you're sending something to the surface of Mars, you have to have it able to cope with that type of environment. So, so Mars is now cold and dry and really harsh for life on the surface. And that's why we want to drill underneath the surface with the Rosalind Franklin rover, which I'll talk about. But how do we know that Mars actually had water on the surface? So I mentioned the indirect evidence. So lots of orbiters have been able to see the signs of water on the surface. But more recently, starting with NASA Opportunity in 2004, which landed on the surface successfully, it's been possible to see direct evidence for water. So we can see in that middle image that's being shown here, it landed actually in a crater on Mars. It's a bit like an interplanetary hole-in-one to actually get to get the spacecraft in that crater, because those are sedimentary rocks on the towards the horizon there that you can see in the middle of the image, and so that's the first time that was seen on Mars. So if you move the rover and actually go up to those sedimentary rocks, you can, and with the instruments that were on Opportunity, you're able to do some mineralogy to see what minerals are there. So for example, the alpha proton X-ray spectrometer on that bottom left-hand image, what happens here is that a radioactive source is taken and you're looking what comes off, and these peaks are to do with particular elements in this case. So the big peak there in the middle is to do with iron. No surprise that there's iron on the surface of Mars. Mars is the red planet because of iron oxide. So things like iron and other metals are seen there as well. But the things with the white boxes, things like sulfur, bromine, and chlorine, those are more refractory, and it's most likely that water would have taken those there. So that was a sort of first indication of direct evidence of water having been involved. And even more from another instrument on Opportunity. This is a rover, so it can move along to the rock, so it did that and got very close to it. And again, you're taking a radioactive source, moving that, in this case, backwards and forwards with respect to the target and looking at what comes off. And so those coloured peaks there are to do with particular minerals on the surface. And so this, one of those is to do with jarosite. So jarosite has a lot of water in it, so there's OH6 in the chemical formula for that mineral. And so again, this is the beginnings of direct evidence for water having been involved in the formation of rocks on Mars. And so that indirect evidence from looking at the topography of Mars is now backed up by in situ evidence of water having been involved. Going on to NASA's Phoenix mission, which was there in 2008. So this landed near the North Pole of Mars. It had this scraper, which it was able to scrape away at the surface, a few centimeters underneath the surface. And what you see on the right-hand side is what was revealed when it's basically sort of digging a small trench. And so immediately that was made. The first image was taken. There's two images being sort of superimposed on top of each other on that. They're taken a few days apart. So the first one shows those on the bottom left in the shaded part of the trench. You can see these sort of globules. That actually is water ice. So that is to do with permafrost underneath the surface of Mars. And there's some more water features on the right as well. So again, near the poles of Mars, there's evidence for water underneath the surface in the form of permafrost. Also, another NASA mission, the Odyssey mission, was able to do a global map of hydrogen underneath the surface using a neutron spectrometer. And so the hydrogen is thought to be in H2O, of course, water. It's sensitive to the first meter underneath the surface of Mars. And so there were particular areas, including the polar caps, but also 3 locations near the equator, where there was a significant amount of this hydrogen indicating water underneath the surface of Mars. So the evidence is really building with these missions for water on Mars. And more recently, the Curiosity mission, Mars Science Lab, which is still working on the surface of Mars, are still sending back amazing results. But I've picked out this one. This is evidence for an ancient lake and stream deposits on the surface of Mars in this particular location. And so the top one shows the image of where this was done. This looks a little bit like mudstones to a geologist. And again, from water about 3.8 billion years ago, that's the signs there. And on the right-hand side, this is a sort of artist's impression of what a lake might have been like associated with that. So basically some some samples were taken by drilling a few centimeters underneath the surface to actually sort of analyze this. And that showed that, yes, water must have been at that location. Not only that, that scale bar on the bottom right is 25 kilometers. So that particular water feature was about 75 kilometers wide. So quite a large area. And this is direct evidence now for this. Also, the acidity, the pH of that water was about right to be habitable. So it would have been suitable for microbial life. So recently, also, just in the last week or so, there's been evidence from Curiosity for water more recently than the 3.8 billion years ago, but more episodic. And so that's an interesting paper as well. But these are all building up to the idea that Mars used to be warm and wet, and so it could have been habitable at that time. So another paper, actually just a couple of years ago, showed using Mars Express, the European Space Agency's Mars Express, showed signs for liquid water underneath the south pole of Mars. And so the image on the left there shows the south pole of Mars in an image. So it's just a little bit below there. You can see this area with those blue patches in the middle image. That's to do with radar, which it's a subsurface sounding radar, which the indications are that there's a lake, 1.5 kilometers underneath the surface of Mars. So this is the first time, really, that liquid water has been absolutely proved to be underneath the surface of Mars with that type of work. And so on the right-hand side, you can see a cutaway drawing using that subsurface sounding radar to see where that water lake actually was. And so that was an amazing discovery as well. So all of this leading to the idea that water certainly was on Mars. And not only that, some water on Mars is still there today. And so some of the water has gone underneath the surface in the form of permafrost and in the form of this lake underneath the surface, and there may well be others which we haven't heard about yet. But there's certainly water in the Martian environment. And so this is giving us a good indication that some of the water is still at Mars. But also, some of it has been blown away by the solar wind. And so this diagram shows what happens when the solar wind interacts with different planets. So I should say the solar wind is a stream of material about 1 million tons per second, a plasma coming out of the sun. So this is the fourth state of matter beyond solid, liquid and gas. So there's ions and electrons, both of those moving outwards from the sun, so you don't get a charge build-up, but the whole thing is moving out and expanding through the solar system and interacting with anything that gets in its way. So on the left-hand side of the image there, those 4 panels show the Earth, but also Mercury, Uranus and Neptune, Saturn and Jupiter. All of these have magnetic fields. They have magnetic fields now. And so the Earth, of course, we know that has a magnetic field at the moment. We used to use that for navigation. Homing pigeons and things like that still actually do use that for navigation. We use GPS, of course. But the Earth has a magnetic field, and that protects it and its atmosphere from the solar wind, and you can see what's being shown there actually is the magnetic field of the Earth. The Earth itself is tiny on that picture, and what we're seeing is what's called the edge of the magnetosphere is called the magnetopause, and then upstream of that is the bow shock. So that's the sort of solar wind and how it interacts with the Earth. And that's spectacular. I mean, it can produce the aurora, the northern and southern lights, so amazing in itself. But the role of the magnetic field here is to protect the Earth from both the solar wind itself, which can pull away atmosphere, but also from cosmic radiation and solar energetic particles. So we're protected to some extent on the Earth's surface from those. Okay, and so a similar story at Mercury, and going down in size there, and then going up in size through Uranus and Neptune. Really exciting magnetospheres those have, because the magnetic axis and the spin axis, in the case of Uranus, is tipped, and the magnetic axis is at an angle to that. So you get a corkscrew effect of the whole magnetosphere, but that's another story. But Saturn and Jupiter, enormous magnetospheres, so you can see the size of those there. So if you look at If you were able to see Jupiter's magnetosphere in our sky, that would be many times the size of the subtended size of the sun or the full moon. So enormous magnetosphere. So the magnetized objects on the left-hand side, there's some protection from the solar wind and from those other energetic particles. Whereas unmagnetized objects like Mars on the right there, and also Venus, Mars, Pluto, and comets. All of those are unprotected by a magnetic field. Comets, we had, of course, a number of missions to comets, including recently the Rosetta mission, and a while ago, of course, the Giotto mission to Halley's Comet and to Griggs Skellerup, and we're showing the size of those interactions on that picture. But Mars, with that tiny interaction, the solar wind can come along, and the top of the atmosphere of Mars is ionized, so there's an ionosphere, and some of that material can be pulled away. So that has happened over time. And in fact, the next image shows an idea of how that happens. And so this is an artist's impression of the sun at the middle of the solar system there interacting with Mars. So both Mars Express and NASA's MAVEN mission have made amazing measurements there, showing the escape of particles. And this is an idea of that happening. So you can see the solar wind coming out from the sun in the middle of the solar system and then interacting with Mars and pulling away its atmosphere. So that magnetic field of Mars was lost about 3.8 billion years ago, and then this atmosphere has been pulled away ever since. So as I say, with Mars, we have this idea that there's some water in the, underneath the surface of Mars, and then some has escaped to space over time, and so we have to take all that into account. And this solar wind has pulled the Mars atmosphere away. Okay, so this gives us the idea that Mars used to be a very habitable planet, what we think is probably habitable 3.8 to 4 billion years ago. So that image on the left gives you an idea of a model of what Mars might have been like at that time, with continents, oceans, water on the surface, clouds in the atmosphere, very Earth-like at a time, as I say, when life was starting on Earth. Whereas Mars now, much drier and less habitable, and actually harsh to life on the surface. So this is why we're looking for past life on Mars with the various missions. Okay, so was there life on Mars? So it's a possibility. So when Mars was warmer and wetter, 3.8 billion years ago, there was some evidence announced by Chris McKay and colleagues from meteorite Allen Hills 84001 back in 1996, for those of you old enough to remember that. But many people found that unconvincing and find that now unconvincing based on the evidence that actually this is probably to do with terrestrial contamination as the meteorite came through the atmosphere and ended up landing in Antarctica. So we must go to Mars to find out. The bottom right image was initially interpreted, that's a scanning electron microscope image of a sample inside that meteorite. Some people interpreted that as to do with potentially life on Mars, but that is now thought not to be the case by most, not all, but most of the scientific community. So we have to go to Mars, and so the missions which are planned are to look for life on Mars and look at habitability. So we should remind ourselves, what do we need for life? So there's a few things, the sort of recipe for life, if you like. So liquid water is obviously very important for life on Earth, and we have the essential elements which are important, so carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. As I say, that phosphine detection at Venus is very interesting with this in mind. You need a source of heat for life, and you need enough time for life to develop. So you need all of those things. And the image on the right there of early Mars showed that it probably had the right conditions at that time. And the image I showed at the start of the talk with those other objects as well, some of those might actually have the conditions for life now. But Mars, we're mainly looking for life which is in 3.8 to 4 billion years ago. But if there were simple life forms now there now, we would still be able to detect them. So Mars Express, the European Space Agency's Mars Express, which went into orbit on 28th of January 2004, that is able to look at the atmosphere and of course look at the surface of Mars as well with a stereo camera, but we're looking at water in the atmosphere, underneath the surface with that subsurface sounding radar which I mentioned, and we're also looking at the escape to space. So we were involved in the Aspera 3 instrument on Mars Express, which is still measuring the escape to space. That's still going very strong. Also, so on the bottom right there, that is a picture of the Mars Express orbiter. That actually took Beagle 2 as well to Mars, which previous Gresham lecturer was the principal investigator for Beagle 2, Colin Pillinger. That tried to land on Mars successfully on Christmas Day 2003. And recently, in the last few years, it was discovered that actually Beagle very nearly worked, but not quite, very tantalizingly close. And we were lucky enough to have done the stereo camera system for that, which put us in a good position for ExoMars. So actually, the technology we developed was actually used in the future mission. So that was great. And of course, so close and so tantalizing that Beagle didn't quite make it, or did make it to the surface, but didn't unfortunately send the data back. But one of the interesting things which Mars Express did find was methane on Mars. And so methane, it measured trace concentrations of methane, and this really is trace, 11.5 parts per billion. So this was measured by the planetary Fourier spectrometer. And that confirmed measurements from the ground as well, which seemed to indicate methane as well. So methane was very exciting because it's expected to be short-lived in the Martian atmosphere. It should only last for hundreds of years. It would be broken up by sunlight, and so it's exciting that it's there. Because it means there must be a source there now. So that source could be geothermal activity, which we didn't really know that Mars was active enough to produce that. Or really excitingly, perhaps it is even life. Methanogens and things on Earth produce methane in swamps, and so that's the type of thing perhaps which could be there. But we don't know which of those two is actually the right answer. So they're very tantalizing results. This means methane was also seen by Mars Curiosity, which is on the surface. So the first paper actually did not find methane, but the second paper did find methane on Mars using the SAM instrument on Curiosity, which looks at atmospheric samples and surface samples, but it analysed the atmosphere and showed there's methane. And in 2018, they showed that actually the methane seems to be seasonal, as seen at Gale Crater, which is their landing site. So it seems to be very, very exciting. But the odd thing is, it's not always seen. So, for example, there is a European Space Agency mission, the Trace Gas Orbiter, which was sent particularly to look for signs of methane. And so far, that hasn't seen it yet. So there's something odd going on. Maybe it's sensitive to the instruments that are only sensitive above a certain height, because that methane is seen by Mars Express and still seen by Mars Express. In fact, there are some times where you simultaneously see methane from the surface, from Curiosity, but then you also see it from Mars Express as well, and so you do see those simultaneous measurements, so it seems to be there. But the methane mystery really for Mars continues, so we're not 100% sure, well, we don't know, we haven't got the evidence to know exactly what is causing it. And this has some parallels with the phosphine discovery at Venus last week. So it's very similar, because that, again, that could be caused by other things, but then the other thing that it could be caused by is life. So perhaps phosphine, is to Venus as methane is to Mars. But methane at Mars is certainly one of the very exciting measurements as well. Okay, so a number of missions to Mars either are going on or are planned for the future. So we have the European Space Agency and Russia working together on that trace gas orbiter, which I mentioned. So that is looking at methane and other trace species. It's also looking at water and water isotopes, heavy water and those types of things, and making amazing maps of those, and is able to also to look at in stereo on the surface with some very nice images. So the trace gas orbiter has arrived at Mars and is making its measurements, but it hasn't yet seen the methane. So that's something to look out for. ESA and Russia are also working on the Rosalind Franklin rover, which is the one on the right-hand side. So that's the one I'm mainly going to be talking about in the talk here. So that is to be launched in 2022, and that will be drilling up to 2 meters underneath the surface. That harsh surface of Mars, we're going to be able to drill up to 2 meters underneath the surface to look for signs of life. So NASA also has the InSight mission, which was launched in 2018, is now on the surface measuring things like Mars quakes. That is not looking for life, it's looking for the interior structure of Mars, geophysics, and doing that type of thing, and has amazingly found some Mars quakes. There's some UK involvement in that mission as well, in terms of producing one of the seismometers. But this year is a very busy one at Mars. There's 3 missions actually which are on their way. So first of all on that list is Perseverance. So that's what used to be called NASA Mars 2020. That's a NASA mission. That will cache samples in their landing site area, which is called Jezero Crater on Mars. So it will cache samples, about 30 different canisters, ready for a future sample return mission, which NASA and the European Space Agency are going to work together on that sample return mission to bring samples back to Earth, to be able to actually do in Earthbound laboratories the types of measurements you could only dream of doing on the surface of Mars. So we can do some things on the surface, but we can't do everything we would like. So bringing samples back is what the Perseverance is the first step in that. Also on the way is the UAE has launched its mission. So that's the HOPE orbiter, launched in 2020. So that gets there next year as well. It takes about 9 months or something to get to Mars. And so that will be making some atmospheric measurements from the orbiter in a particular area of science of the atmosphere, trying to link really what's the lower atmosphere to the higher atmosphere, so very exciting. Also China has the Tianwen-1 orbiter and rover, launched in 2020 as well, so that is going towards the surface of Mars as well. But none of those missions, apart from Rosalind Franklin, is going to be drilling underneath that harsh surface of Mars to look for signs of life. And so that is a really exciting mission. That's why we're so excited about being involved in it. And actually that rover, the payload of it, the instruments of it, are shown on this graph. And so on the left-hand side are the various context instruments. So they're trying to plan where to drill, basically, to see where to go, where to drill, in the Oxyaplanum landing area, which has been selected for ExoMars. So we have PanCam, which is our panoramic camera system. So I'm the lead of this, and we have a big team in the UK and in Europe, so particularly Germany, Switzerland, and Austria involved in this very strongly. And so there's also the infrared spectrometer that will look at one of our pixels from our high-resolution camera and extend the measurements into the infrared. So with that, we'll be able to do very good mineralogy. There's WISDOM, which is a subsurface sounding radar looking for water ice again, but also looking at rocky outcrops under the surface, good places to drill. There's ADRON, which is looking for that hydrogen underneath the surface. So that is using the same neutron technique that Mars Odyssey used to be able to see the water and hydrogen underneath the surface of Mars, and they mapped it out, if you remember. So this is doing that locally. There is also a close-up imager at the bottom there in the context instruments, and so that is a bit like a sort of geologist hand lens to be able to peer at rocks very closely, to be able to see features on them. In the middle, there's another instrument. So this is a tiny imager and infrared spectrometer, which is actually integrated into the drill itself. So the drill will drill down up to 2 meters underneath the surface, as I say. Inside it is this little spectrometer, which will do the local geology for where the sample is actually got from. So we get a sample, bring it out from underground, put it in what's called the analytical drawer, and they're analyzed. So the analytical drawer instruments on the right-hand side, so we have micrometer, which is an visible infrared spectrometer. There's a Raman spectrometer, so that looks at fluorescence and mineralogy. That has some UK involvement as well from the University of Leicester and from Rutherford Appleton Lab. There's also MOMA, that's the Mars Organics Mass Analyzer. So this is the one with all of the other instruments which are really looking for biomarkers, signs of life. And so that's actually what we're looking for, biomarkers. So MOMA will be able to look at things like carbonates, look at things like amino acids, phospholipids, things like that. And so it will be able to do that. It will also be able to do chirality, so that's looking for left-handed and right-handed molecules. One of those is used by life on Earth, one isn't. So it's very well instrumented to be able to do that. And as I say, the key thing, being able to drill underneath the surface for the first time. So this is a little video about the Rosalind Franklin rover. So basically our plan is to launch this on the 21st of September 2022. It will land on the 10th of June 23, and it drills up to 2 meters underneath the surface. So that's the new thing. And it has these instruments. So just while we have this image here, at the top of the mast that you can see there, that is PanCam. That's our panoramic camera instrument. On the front in black, you can see the drill, of course the wheels at the bottom, the solar panels. It's a solar-powered rover, so it is going to be using sunlight for power, which means you have to land near the equator on Mars. But all of those instruments will work together. And I have to say, actually, this was... the rover was built not far from here in Stevenage. Airbus Defence and Space in the UK were the lead for the rover. Thales Alenia in Italy are the prime contractor for the whole mission, but the rover itself was built in Stevenage. And so lots of UK, both industrial and academic involvement in this mission, which has been particularly good. Okay, so the video actually gives you an idea of what the rover looks like from all angles. So you can see PanCam at the top there, the black drill at the front, at the back, those orange things are the WISDOM antennas to look underneath the surface. We also have there's the drill moving to bring possibly a sample into the analytical drawer. So that analytical drawer is at the front of the rover, and the analytical drawer instruments are inside the rover. So we do the analysis inside there, send that back, and scientists analyze them to look for signs of biomarkers. So that's the rover, and a very exciting mission. And of course that is planned, as I say, for launch in 2022. So here's some of our team in pre-socially distanced times back in December 2019, when we were able to meet together in the European Space Technology Centre in Holland, and here's some of the team. The reason for showing this is to show you basically the size of the rover, and so you can see our camera system, PanCam, sits about 2 meters above the surface, and you can see that's a 1-to-1 scale model of the rover there, and it's great to be able to see that in situ. Okay, so this was a test of the parachute system. The parachute system is something which initially there were some problems with, but in 2019, this is December 2019, these seem to be solved, and so the hope is that the parachute system will work very well. This is the largest ever parachute to be sent to Mars on this mission, so it's important it works right. It's got to deploy correctly coming out of its system, and this shows some of the testing which was done on that in Oregon. We've got some more tests coming up of that in November this year to make sure things are all fine. So that's one of the things, because originally we were hoping to launch ExoMars this year, but that's one of the things which delayed it. Some other technical issues, and of course the virus didn't help either. Okay, so why do we call it Rosalind Franklin? So this is an amazing name for our rover. She, of course, a wonderful, brilliant X-ray crystallographer whose famous photograph 51, of a fibre of DNA were important in the discovery of the double helix. And so this is an amazing thing. So photo 51, you can see that on the bottom left there, very famous, and some of her notes there about DNA. So I wonder what our photo 51 will see. We'll have to wait and see. But she also did lots of other important work on the structure of carbon and indeed viruses. So, very relevant work. And so it's very appropriate that the rover is named after Rosalind Franklin, and so we refer to it with her name now. Okay, so this sort of drives home the reason why we want to drill underneath the surface, and this is the main point of this mission. So that we have the penetration of organic destructive agents being shown here. So we have to drill basically up to about 1 millimeter to get underneath that surface, which is bathed with ultraviolet radiation. We have to get below about 1 meter to get below oxidants, things like perchlorates, which could be a problem for looking for biomarkers. And then we have to get below about 1.5 meters to be able to get below where the radiation is penetrating to. So the best preservation would have been below 1.5 meters. We actually did some calculations with an ex-PhD student a while ago about this, and 1.5 meters is at least, you have to drill at least that to be able to get good samples from underneath Mars. And so this is why that 1.5 meters and 2 meters is very important for our mission. Okay, so where are we landing? So Oxyoplanum, so this was put together by one of the colleagues on the team, gives you an idea of where on Mars we're going to be landing. So it's between that low terrain in the northern hemisphere, the younger terrain, which possibly there was an ocean there, and then in the southern hemisphere, those are the southern highlands. So it's in between those two. There's lots of history of water from orbit. Clay-bearing rocks have been seen. 3.9 billion years old. There's remnants in this region of a fan or a delta in this outlet of this Cogoon Vallis region, and so it's an exciting place to land. Those are the landing ellipses which are shown there. Those are the accuracy with which we can land in that area, and so the choice of that landing site it's not only scientific constraints of an interesting place with history of water, but also those engineering constraints as well of being able to operate solar panels and to give the parachutes long enough to work in the very thin atmosphere of Mars. So that means you have to land below a certain distance. But at the end of the day, it's science, and actually fantastic landing site has been chosen. That was narrowed down a few years ago now, and so that's the landing site which is planned. Okay, so I can't get away without talking about our own instrument. So this is PanCam, the panoramic cameras, the scientific eyes of the rover. So inside of it, we have 2 wide-angle cameras, which are separated by 50 centimeters. So imagine that sitting 2 meters above the surface of Mars. You can get better stereo reconstruction than we can do with our human eyes with that. Each of those has a little filter wheel in front of it, which has 9 filters in, with which we do geology and atmospheric science. We also have a high-resolution camera in the middle there. That's effectively, we can look very closely at rocks. It's like a telescope or a telephoto lens, looking at particular features of rocks to be able to get that geology. There's the electronics to run that, and that all sits inside what's called the optical bench on the top of the mast there. But also there's the small but important items which are important as well. So the calibration target, so we have a colored calibration target to get the colors right on Mars. We have fiducial markers to get the shapes right, and we have a rover inspection mirror with which we're able to actually see underneath the rover for engineering reasons, to be able to get... so with this as a whole, we're getting stereo, colors, shapes and scales. And so it's an amazing instrument. So this is just who's built the different bits of it. So, so our lab has built quite a lot of it, but also our colleagues in Switzerland and Germany have built the actual cameras. Aberystwyth University has been involved in the small items, and we have a 9-nation science team, so very international work. On the right-hand side, I can't, not show images of the team who actually built this. So the top right, that's the core engineering team, which were involved in the delivery of PanCam last year to Airbus. And so that is now, that's been integrated with the rover, which is now in Turin. And on the bottom right, that's our science team, which we had a meeting earlier this year, but also we've actually got one tomorrow and the day after. Okay, so the filters, and I love showing this. These are the actual filters which are going to be looking at Mars. So these are the ones on the flight models on the actual cameras. And so the particular wavelengths in the visible are shown there. So we have 11 of these filters on each wide-angle camera. So these are effectively selecting out colors to look at. So with geology, we'll be able to look at water-rich minerals, very accurate representation of water-rich minerals with minimal error of determination. And so one of our ex-PhD students, she helped us to work on that a few years ago. And that, so we've implemented that. And then we have atmosphere filters as well. We're going to be able to look at water vapor. So we look at a particular absorption feature of water. And if you can imagine a sunset on Mars and looking at sunset as the sun goes down, looking at the sun, with looking at the depth of that feature, we'll be able to see how much water is between the sun and us. So that tells us how much water is in the atmosphere. We'll be able to compare that with atmospheric models and compare with escape to space. So we have a couple of new students who will be working on that topic. We also have the high-resolution camera that not only is looking closely, it's also in color itself. We have a biofilter on that, and so that provides the rock texture. So a couple of impressions of that, and so these are the actual sort of from the engineering drawings. You can put the computer-aided design model together, and so this was put together by a colleague, and so you can see again the filter wheel at the front there, and that's the 11-position filter wheel. Each of the two wide-angle cameras 50 centimeters apart, and the high-resolution camera in the middle there. And this is what it might look on the surface of Mars, and so our colleague from Helen from Aberystwyth has done some renderings to be able to show what it will look like, and that's PanCam white painted so that it doesn't get too hot during the day, and also it has heaters to make sure it doesn't get too cold at night. But we've had to really put this through the test to make sure it will survive this incredible environment on the surface. So not only the launch itself is a difficult environment. The landing, of course, is a difficult environment as well with vibration and shock. But also the temperature on Mars, going down to that very low temperature at night, means that we have to be very careful that everything works for that. So lots of testing has been done by our amazing engineering team, and we have a big science team behind this as well, as I say. So the reason we want to do it is science. We've stuffed as much science as we can into what is basically a camera instrument for going to Mars. And these are just some examples of how we've used that in the field. So examples of use of PanCam. So it's been to, the emulator has been to a number of different places. So Iceland, the Utah desert, other places to be able to test it, and also to test the team to make sure the team is working together in the right way for doing analysis the way we're going to do it. Because for a Mars mission, you basically have a downlink at the beginning of the day. That's the information sent back from the rover from what it had the day before. You then have a bit of time to work on it to get to work out what to do next, then to send the commands for the next day, and then you go off and do that. And so it's all driven by the orbiters which are in orbit around Mars and when you can get the data back. So basically you have that daily structure for what is going to happen. But the science we'll be able to do is exemplified here. So on the bottom left, you have a 3D model. As I say, this is better than the human eyes can do. And on top of that, some of our colleagues, geological colleagues, have put on what's called dip and strike. So with that, you can look at sedimentary rocks and see how they connect to other sedimentary rocks and so on. That's on the bottom left. On the bottom right is something called principal component analysis. So that uses those detailed filters with the narrow filters of which we're able to look at geology and look at the ratios between those to be able to work out, again, the mineralogy and the composition of the rocks. So you're sort of using colors to be able to get the information about the minerals which you're looking at. We can also, with PanCam, we can image the sample before it goes into the sample collection hole. We can also look at the drill tailings once the rover has moved back from where the drilling was done. So it's a very important scientific part of the rover system. Okay, so this gives you an idea of the type of quality which we'll be able to get, hopefully from the surface of Mars. So this particular panorama of a number of different wide-angle camera images was taken in a trial in the Utah desert in 2016 and written up in that paper which is shown there. And actually, I should say there's a lot more references in the transcript if people are interested in looking at those. But on the surface there, that gives you an idea of what the quality of the images on Mars are going to be like. We don't expect, of course, as blue a sky as that. That's something to do with, of course, scattering in the Earth's atmosphere. But we have the calibration target to be able to get the colors right on Mars. Okay, another trial in the Atacama Desert in February 2019. So that's an image there on the left. And then using the image, detailed image on the right, it was possible to use some wide-angle camera to get some spectra to be able to, again, work out the mineralogy. And so one of our collaborators has been busy with that, Elise, at St. Andrews. And so again, the 3D image there. So this is going to be a little video of the landing sequence and what happens just after. So I'll sort of talk you through this. So this is the air shell which stops the spacecraft burning up as it hits the top of the thin Martian atmosphere. So then the first parachute deploys, and then the second parachute deploys, and the structure floats down on that. The back shell is released, and then the rover is released. And so this is the rover on its landed platform, which is called Kazachuk. That's one of the Russian parts of the mission, which also has some science instruments on board, but the rover is on top of it. So you can see it's using retro rockets to actually land safely on the surface of Mars, and so it will be doing that in 2023. So after landing, the solar panels are deployed like this, and then that's the landing platform. These are the ramps in the front, solar panels deploying again. And so with that, we eventually deploy the mast with PanCam and ICEM on the top of it. So at the top we see PanCam, the infrared spectrometer is just below, and then the navigation cameras, which have obviously for navigation, are on the on the front there. So we scan the Martian surface, and then hopefully move off down the ramps. Now all this is really speeded up. The actual speed of the rover on Mars is maximum, absolute maximum, about 3 meters per second. So you know, this is very much speeded up, but it gives you an idea of what we're going to be able to do. So we have wheel walking, so you can avoid rocks and things like that. That's been implemented, and there's some autonomy on board to be able to avoid rocks. We also have the camera to look at that. So when it finds a good spot from all the instruments, the context instruments, we drill down into the Martian surface and look at get the sample and put that into the analytical drawer, and that is put into the rover for analysis. So as I say, that will all take quite a long time. The complete mission is 218 days on Mars. The sol, or day on Mars, is just over 24 hours, and it takes you know, there's 218 sols for the entire mission. Okay, just a few images to finish off. So this is the integration of PanCam at our laboratory. And so this is the electronics actually going into the optical bench there. You can see the filter wheels on the side just before integration there, going into the instrument. You can also see how it's important to be careful. We have to make sure that we're not taking life from Earth to Mars. So the clean rooms are extremely clean, and we do swab tests and so on, which we're getting all too familiar now with now, but to make sure that we're not taking life to Mars. So everything has to be kept very clean. These are some of the images associated with the delivery on the right-hand side. But on the left, so we delivered to Airbus in May 2019. It was installed in the rover in August last year. Bottom left-hand side, you can see this is an image of the filters before they were actually put into the filter wheel. So this is a little bit like contact lens cases. And so the European Space Agency did a special picture of the week about that last year. Okay, so PanCam on the rover. I'm so proud to be able to show this because this is on the rover itself. The rover has been built in Stevenage. This test actually was done in Toulouse. The rover is currently in Turin, and that shows the optical bench and the small instruments on board the rover. And just the last couple of images. So this is the installation of PanCam onto the mast. And I think this is amazing. This is the first light image. So this is my colleague Matt Gunn from Aberystwyth holding up a thing to the camera system, all the way through the camera system, and it says "Hello Mars." And so this is our first light image on the rover, everything going through the rover systems very well in August 2019. I'm happy to report it's still working this week. We just had a report this morning of the latest tests which have been done on the rover in Turin before it goes to Cannes for some more tests and then eventually off to the launch site. So just to finish, the Rosalind Franklin ExoMars 2020 rover will provide an important new dimension on Mars. It will drill underneath the surface of Mars up to 2 meters for the first time. And with the other context instruments, this will provide geological and atmospheric context for the mission. So we're really looking forward to it and hope you'll follow with us in 2022 and 2023. Thank you very much.
Thank you very much, Professor Coates, for that fascinating lecture. We've got a lot of questions, so I'm going to go as fast as I can to get through them. The first one I've got here is, using the Drake equation or variation for the likelihood of extraterrestrial life, what is the probability of 2 planets in the same stellar system developing life independently?
Yeah. Good question, and I don't know the answer, but the Drake equation is notoriously difficult because there are a few terms which you can actually determine, but you can't determine all of them. And so you can determine things like star formation rate, planet formation rate. There has been a lot of progress made in terms of seeing the number of planets around other stars. And in fact, all the stars which we can see in the sky at night, when it's nice, probably each of those has a planet associated with them. But yes, putting the numbers in and getting the exact answer to that, I'm not sure. But we're looking for independent life happening elsewhere in the solar system. And so, yes, Mars, the Earth, basically wherever conditions are right. So in our own solar system, we can look at where conditions either are or were right, and then we can take those lessons on to extrasolar planets and all the planets there are elsewhere. And so, but our own solar system is a good place to start.
Great. We've got 2 questions about phosphine and whether there's evidence of phosphine on Mars, and one about why water. Why is it indicative if there is water, there is life, or possibly life on a planet?
Well, water is very important as universal solvent and very important thing for the generation of life, and so water is seen by everybody to be very important in that. The phosphine thing, certainly, people have looked for that type of thing. As to whether phosphine has been discovered, I would have to look through the literature to be sure about that. It's a very good question, and of course very topical based on the fact that there's phosphine at Venus. But as I say, methane is a thing which we have found, which seems to be doing a similar type of thing at Mars. But it's an interesting question about phosphine, though. Yeah.
I've got a question here about temperature. What changed the temperature on Mars from warm to cold now? Is it the formation of the planet that was creating the warmth?
Well, yes. So yes, there's a number of different sort of timescales there. But yes, way back in the beginning of the solar system, Mars was smaller than the Earth. Well, you know, still is, of course, but smaller than the Earth, and so it lost its heat of formation more quickly than the Earth did, which means that there was less heat around to effectively keep the magnetic field going. I mean, the motions in the core, the iron in the core producing the magnetic field, that's still, of course, going at the Earth. We have magnetic reversals and things like that, but it's still going. But on Mars, that stopped. So that's the big time scale. I think, you know, on the daily time scale, of course, going from day to night, it's the fact there's a thin atmosphere. So the atmosphere produces some heating at Earth, and of course, you know, the reason why we have usually temperate conditions on the Earth's surface is because of our atmosphere. And so if you have a thin atmosphere, you have these extremes of temperature. So going from you know, 10 degrees maybe on the day side of night to minus 100, 120 at night, that's expected. It also varies with the season as well on Mars, as Mars goes through its season. So yes, a number of different timescales.
Great, thank you. And I've got another question here about the lack of magnetic field on Mars, asking what safety measures would need to be done to allow a manned mission to Mars. Could this be done with current technology?
Yeah, manned missions to Mars, yes. I mean, there's a number of things, of course, which you need. I mean, not only the technology to launch people, the life support systems, etc., which you need to be able to take them, but yeah, the protection once you get there. So yes, Mars doesn't have a global magnetic field, which means that radiation environment is worse on the surface than on the International Space Station, for example, or indeed on the surface of the Earth. And so that the fact that you have that lack of magnetic field means that it's challenging. So you might choose to land on one of the anomaly or crustal magnetic field sites, but that is difficult to do because that's in the Southern Highlands region, which is you know, you don't have enough time to actually do the parachute work to get it down there safely. So there's lots of different challenges with sending people to Mars, and you know, apart from money, which is huge, you know, and personally, you know, I think actually we should wait with a manned space exploration until we know the answer to this question of was there ever life on Mars. After that, maybe, you know, if the political and industrial will can be made, then eventually maybe. And there are plans, you know, potentially to do that, but I would, on the scientific point of view, prefer to wait. And I certainly don't want colonization of Mars, which is another thing which some people would like to see.
And I've got another question here about the geothermal activity source of methane. Would it be compatible with the fact that Mars's magnetic field has extinguished? Aren't both related to a flow of liquid and metal around the core, like in the Earth? Well,
there's certainly a liquid, the flow of liquid around the Earth is, of the liquid core around the Earth is important in driving the magnetic field, absolutely. And so sorry, what's the first part of the question again?
Would the geothermal activity source of methane be compatible with the fact that Mars's magnetic field has extinguished?
Okay, well, the idea is probably that this geothermal activity would be relatively small scale rather than a huge, large planet scale activity which would be necessary for producing a magnetic field. So it could be small scale features of activity still do exist. And in fact, you know, there are other indications on Mars that there are, you know, there is small-scale activity. So there could be that. There's also signs of fairly recent volcanism, you know, much less than the 3.8 billion years ago. And so there are signs of kind of local activity going on, but not planet-scale things which you would need to actually drive a magnetic field.
Okay, great. And I've got a question here about the parachute.
Yeah.
What aspects of Mars make the parachute so difficult to engineer?
Yes, well, the fact is the thin atmosphere on Mars means that it's one of the most difficult places to land of any object in the solar system. Because if you have an airless body, like the Moon, you know, which only has a really, really thin atmosphere, you know, it's not an atmosphere, it's more of an exosphere. But on Mars, the atmosphere is thick enough that you have to slow the spacecraft down using, and you can use parachutes to do it. But because it's the thin atmosphere, they don't work as well as they do on Earth. So you've got to make sure with the parachute testing which is done, that the parachute will work in the environment which it's designed for. So as well as the tests which are done on Earth in Oregon, for example, we also have some high altitude drop tests planned in Kiruna in northern Sweden next year. So in that, you're going effectively to stratospheric altitudes, and that's about the right pressure for where it will be doing its stuff at Mars. And so it's the pressure of the atmosphere which is causing the difficulty. The fact it's intermediate between a thick atmosphere and a thin one. So at Titan, for example, the Huygens probe had parachutes as well, but that atmosphere was about 1.5 times the Earth's atmospheric pressure. So while the engineering was challenging, because of course that's an alien atmosphere as well with nitrogen and methane, the pressure though was about a little bit higher than the Earth's atmospheric pressure. But for Mars, yes, it's a big challenge.
I'm afraid we are now out of time, so there is one more question which I will send you from online for later. Okay. But thank you so much, Dr. Coates, Professor Coates. Thank you very much to our audience for your attention and questions. We'll be sending you a link to the video and transcript very soon. Our next astronomy lecture is Cosmic Vision, Watching the Radio with Professor Catherine Blundell on Wednesday the 7th of October, 1 p.m. to 2 p.m. And you can sign up for that online now. Thank you so much, Professor.
Thank you.